Yes, good evening, everyone. Welcome back.
Good evening, sir.
Good evening, sir.
So, gone through the lecture, Dinesh?
Yes, sir.
Okay, understood
Yes,
everything?
sir.
Understood everything?
Yes, sir.
Okay, okay. So, we'll wait for others also. So, we'll begin the session soon.
Yes, sir.
Any doubts, Shweta, from yesterday's class?
No, sir.
Okay. As of now, no, right?
Yes, sir.
Okay, okay. So, yesterday we discussed about two important biasing techniques. One is source biasing, correct?
Yes, sir.
Another one is voltage divider biasing, correct? The last one. Only three biasing techniques. One is gate biasing, gate terminal, biasing through the gate terminal and using gate resistor, of course, and biasing using source resistor. So we call it a source biasing. That is the one widely used. And finally, the even widely used one is voltage divider biasing. That's universal. This is always an universal biasing technique. So we discussed about that design only and hope you made the analysis for this problem. Shweta, Dinesh.
Sir,
Yes, Shweta.
sir, same way how we done in source biasing and I done, sir, but
Answer is not coming.
yes, sir.
Okay.
Sorry.
Okay, different response you're getting than the design one, right?
Yes, sir.
Yes. Dinesh, have you tried this?
Yes, sir.
What is the answer you're getting for this?
Sir, but it slightly deviates from the
Deviating, huh?
from the
Okay.
design. Yes, sir.
Okay, we'll check where the mistake happened in our design or in the analysis. We'll see. So anywhere there is a mistake, either in the design part or in the analysis part. Okay. Yes, gate current is 0 always. So the potential at this point is equal to the top is 20 and the bottom is 0. So the net difference is 20 volt across this, correct? That will make a current of 20 across 20 mega ohm as 1 microamps. So either you focus on voltage drop across R2 or drop across R1. Okay, if you find the drop across R1, the drop will be 1 micro into 11 mega ohm, it will be 11. So 20 minus 11 will give 9. Otherwise, the same current of 1 microamps is going through the 9 mega ohm, going to make a drop of 9. 0 plus 9. Also, either you go this way or you go this way. The result is what? Same, correct? Getting?
Yes, sir.
Yes, sir.
Okay, that is equal to 9 volts. Okay. So gate potential is known, right? That's a potential you have taken in the analysis. Yes.
Yes, sir.
Then we are looking for the voltage VGS. Okay. So we know the VG, we don't know the VS. So VS can be written as what's the drop across this? Assuming the device is in on condition. Of course, in saturation, because we have the expression only for the saturation. Forget about the ohmic equation. Use the ohmic equation only when it is clearly known as ohmic. Otherwise, by default, you need to assume it is only in saturation. So, assuming it is in saturation, we know the equation for ID. Hope you remember that equation. ID equal to Kn into VGS minus V threshold of the NMOS the whole square. So Kn given, V threshold is given. So assuming the saturation current is there, the current is going to make a drop across this, that's ID into RS, that is going to be plus minus, correct? So therefore, I can say Vs is equal to, it is potential 0, potential rises by IDRS, so Vs is equal to ID into RS. So have you taken Vs equal to IDRS or something else? Shweta.
Same ID into RS, sir.
Okay, then the problem begins. Let us begin the analysis. So the goal is to calculate VGS. So then we know VGS is equal to the gate potential minus the source potential. So therefore the VGS equation, gate potential is 9 volts, source potential is ID into RS, correct? Correct, Shweta? Then the expression VGS, correct?
Correct, sir. Yes.
Then you get 9 minus ID is what? Kn into VGS of NMOS, shortly VGS. Only NMOS is there. Its threshold, V threshold of NMOS, the whole square. That's your ID into what? RS will be there, correct? Getting?
Yes, sir.
Then what is the product Kn into RS? Kn is given 1 milliamps per whole square. Okay. 1 milliamps per whole square. RS is given how much? 250 ohms, correct? Yes.
Yes, sir.
Yes, sir.
But this product for 250 ohm can be perceived as 0.25 kilo ohms, correct? Then milli and kilo will get cancelled. Result is going to be 0.25, correct?
2.5. Yes, sir.
You got this value, Sweta, or something else for this product?
Sir, I didn't cancel that milli and kilo. I got 250.
That's where the problem originated.
Okay. Yes.
Got it? Yes, that's a troubleshooting way. You are going same path. Okay, you're going to walk the same path, but where the mistake committed because you played with ohm and milli, so you should have taken you got the result as milli. So you have to make it as instead of 250.25. That's where the mistake committed. Yes, whether you are correct at this point, Dinesh.
Yes, sir.
Okay, then let us proceed further. So now you understood where you got deviated, Shweta, right?
Yes, sir.
So definitely the result will be different. Now let me go ahead. So it's 9 minus 0.25. So that's Kn into RS. Let me prefer to write it as 1/4 into VGS minus what is the threshold? We don't know the VGS. What is the threshold? 1 volt, correct?
1
Correct?
volt, sir.
1 volt, then
Yes, sir.
substitute that. So it is going to be VGS minus 1 the whole square, correct? Then after taking LCM, so this is 4 into 9, 36, and 4 into VGS. You can take it as 4 into VGS equal to 36 minus what? VGS minus 1 whole square. That is nothing but V square GS minus 2 VGS plus 1, correct? Is this expression you got, Dinesh? Have you got this
No, sir, I
expression?
haven't. 1/4.
You played with the
Yes,
0.25.
sir.
You played with
0.25. Yes, sir.
okay. Anyway, the result has to be same. 1/4 is equal to 0.25 anyway, right? So I'm taking LCM.
sir.
So then 4 into 9 is going to become 36. And the whole denominator 4 is taken to the left side. Then it becomes 4 VGS. So no mistake, right? In this step, correct?
Yes, sir.
Agree, Shweta.
Yes, sir.
Then let us go ahead. So then you take entire right hand side to the left hand side. Entire right hand side to the left hand side. Then what you will get? You will get V square GS minus 2 VGS plus 1 you will get as it is. Okay, because it is a minus of, so push it to the left side. Then minus 36 plus 4 VGS you will get equal to 0 will be the equation, correct? Then simplify this, then you will end up with V square GS minus total VGS plus 2 VGS, correct? Minus what? 35 equal to 0 will be the equation. Getting, Shweta?
Yes, sir.
Now we can solve for the VGS. So VGS is equal to, so which is equal to minus B plus or minus root of B square, that is 4 minus 4 AC. So it is going to be 4 into 35. It is going to be 140 divided by 2A. Then VGS will be equal to minus 2 plus or minus root of 144 is nothing but 12. Yes. Am I
Yes,
right?
sir.
12, right? Divided by 2. Then what are the two roots of VGS? One root will be minus 2 minus 12 by 2. That is going to be minus 7, right? Correct? Another
Yes,
root?
sir. 5 volt.
Minus 2 plus 12, that is plus 10 by 2. Yes, that's what exactly the design value, Sweta. So design is perfectly all right. We didn't
Yes,
commit
sir.
any mistake. Even though
I
we played in the air, correct? We still made the design better, correct? Yes, minus
yes, sir.
7 is a wrong root. Why? Because we know our NMOS is operational only for voltage more than 1 volt, correct? Getting Dinesh?
Yes, sir. Getting, sir.
Okay, yes, therefore the right root is 5 volt, then VGS equal to 5 volt. Then again copy the circuit as it is, know your conditions. Okay, so you know your VGS now. Then play with the circuit, don't play with the equations. You know this potential is 9 volt. You know this potential is now how much? 5 volt. Therefore, lose 5 from 9. You know your source potential. What is the source potential now? 9 minus 5, how much?
4.
4,
4
sir.
volt. Then entire 4 volt will fall across that 250 ohm, correct? Because the bottom is 0. Then what's the current now? 4 by 250. That milliamps, everything is important. 4 by 250, you will get 10 power minus 3, so 16 milliamps, correct? Getting?
Yes, sir.
Okay,
Yes, sir.
that's your channel current. Assuming device in saturation, we are doing this, then 16 milliamps. Then 16 milliamps across 500 will make a drop of how much? 8 volt. Okay, 16 into 0.5 K, 8 volt. Then you are losing 8 from 20. Then the VD is equal to how much? 20 minus 8, 12 volt.
12.
Therefore, in the given circuit, VD is equal to how much? 12 minus 4, how much? 8 volt is your VDS, correct? So 8 volt is VDS. Since VGS is known, then we know our VDS pinch off also. What is the VDS pinch off? VDS pinch off is VGS minus what? V threshold of NMOS. So which is nothing but it is 5 volt minus 1 volt. So it is equal to only 4 volt. Therefore, we can conclude that device is in saturation since what? Since VDS is greater than
VDS pinch off.
pinch off, greater than or equal to VDS pinch off, we can comfortably prove that device is in saturation, then all the responses are valid because assuming okay device in saturation only we got this current. Okay, therefore once you prove it is in saturation, yes, all the responses are valid. That's how the analysis we can do for voltage divider bias. Ready? Easy, Sweta?
Yes, sir.
Easy, Dinesh? Following right?
Yes, sir. Yes, sir. Following.
That's analysis. Okay, so you can also appreciate your design skill. Okay, so first we made the design, then we started doing the analysis. Okay, so refer one of the yesterday's problem. Okay, we played with. We'll take that as an example. So before getting into the next topic, few examples we'll try. One problem where I introduced NMOS and ohmic. Yes. So what is RD we have chosen? 5 kilo ohms. And VGS is given as 5 volt, correct? Let me take the same example. I'm going to make the problem little different. So VG is 5 volt. And what is a KN we have chosen for that device? Okay, KN is 0.5
0.5 million.
milli and threshold is 1 volt. Let me refer the circuit. I'm giving it as a new circuit. Yes, you can do it now. So it has Kn is equal to 0.5 milliamps per whole square. threshold voltage is equal to 1 volt. Source is connected to ground. Going to have a resistor RD excited by EDD, that is 20 volts. Then I'm going to make the circuit slightly different. I'm not going to give this potential. I'm going to connect the gate and drain together. I'm going to connect the gate and drain together. Okay, that's where your problem begins. Find the current in the channel. Find the current ID. Yes, find the current ID in the given circuit. That's all. That's example. Let me supply only the value of RD. $17 kilo ohm. RD is 17 kilo ohm. Yes, that's the data given. So when RD equal to 17 kilo ohm in the given circuit, find the current ID. Yes, you can try. Dinesh and Sweta, yes. Can you answer the problem? How you're going to approach this problem?
VGS need to find.
Yes, VGS is unknown, right?
Yes, sir.
So without VGS, we can't comment on
ID.
ID. Okay, you can also find the VDS. Okay. So VGS also, yes, VGS is the most important thing. Otherwise, we can't comment on ID. Okay, so as per the given circuit, we can make one important conclusion. Let me take it to the next slide. Yes, what is this potential? VGS, correct? What is this potential? VDS, correct?
Yes, sir.
So what is this point potential?
VG.
VG, sir.
No, I'm calling this as VGS means, you know, this point potential is 0. What is this point potential? If there is some certain value of VGS, what is this point potential?
VGS.
Yes, there is a gate potential, but that is going to be exactly equal to what? VGS, correct? So the gate potential is equal to VGS. And what about drain potential? Since drain and gate are shorted, and what will be the drain potential? That means gate and drain potentials cannot be different. So therefore, whatever the gate potential, that is your drain potential. Therefore, VD is equal to VGS. Now tell me what is VDS in the given circuit.
VGS, sir.
VDS equal
VGS,
to
sir.
VGS. Then what is VDS pinch off? VGS minus V threshold, correct? If that is the case, can I prove now VDS always greater than or equal to VDS pinch off? Can I prove that the given in the given circuit device always in saturation? Yes or no?
Yes, sir. Yes, sir.
Getting Sweta?
Yes, sir.
So whatever may be the value of VGS, you're going to subtract 1 volt from that. So automatically the VGS will be greater than. Automatically VGS will be greater than VGS minus V threshold. Correct? Correct? Any doubts, Sweta?
Yes. No, sir. No, sir. Clear, sir.
Clear, right? So therefore, the moment you short gate and drain terminal of any MOSFET or any FET device, always going to be in saturation.
Saturation.
That's another important learning through this simple example. The moment you see gate and drain shorted, by default device is going to operate only in saturation. So the moment you know it is in saturation, straight away you can start playing with the equation ID versus VGS, correct? Correct. The moment you know it is in saturation, directly can exploit. So ID equal to Kn into what? VGS minus V threshold of N mass. But the beauty of the problem is VGS is still unknown. Correct. But without that, still you have concluded the device is always in what? Saturation. Correct.
Yes, sir.
Okay, now let us begin the problem. Since a device is known to be in saturation, so let us begin the analysis. It is clearly known it is operating in what? N mass in the given circuit, clearly operating in what? Saturation. Let us begin the analysis. Okay, so the current is ID. So what's analysis now? Okay, so form a simple KVL in this path. What is the KVL in this path? And this potential is VGS, correct? So the supply voltage VDD is spent only as 2 drops. Okay, one drop is drop across RD. What is the drop across RD for the given current? Because you know very well the gate current is always equal to 0. Therefore, at this node, whatever the current you have in the channel, that's a current here as well. So that therefore it is going to be ID into RD. So the 20 volt VDD is spent as one drop across RD. And after that, it is a short voltage across short between gate and drain is equal to what? 0. Then it is spent as VGS. So shall I write this KVL as VDD is equal to what? IDRD into, because I don't know the VDS. Even VDS equal to what? VGS only, already it is concluded. Even the VDS is equal to what? VGS, you can also go by that VDS, okay? You can also form a KVL in this path, okay? That KVL, you will be writing it as what? VDD is equal to IDRD plus what? VDS, you can write, but VDS also equal to what? VGS, correct? So anyway, both are same equations, correct? Getting? Either
Yes, sir.
you
Yes, sir.
make drain to gate side KVL or drain to source side KVL. Result is same, okay? Correct?
Yes, sir.
So what is VDD? It's 20 volt. Correct? Goal is to find VGS now. The goal is to find VGS. Then 20 equal to what? IDRD. RD is known as what? 17K. We'll substitute later. So then plus VGS. So we have two unknowns. One is ID, another one is VGS. That's all. The circuit is giving only one equation, that is function of two unknowns, but we need to solve for either VGS, but problem is only for the ID. You can solve for ID, but as I told you, it's a field effect transistor, but always make your problem to solve for the voltage only instead of the current, because with the current, it's not easy to discard the wrong root, because it is again going to be a second order equation. If ID equation second order gives two roots, means you should be in a position to discard the wrong answer, correct? Wrong root, correct? So that may not be easy. Okay, it is better to go by finding what? VGS only. Okay, instead of writing VGS as a function of ID, better you go with the ID replaced by VGS. So we have the equation. So ID versus VGS. We'll use that equation again. So then we'll make the entire equation function of VGS. Then we'll solve for it. Okay, that's a plan. So then what we have is 20 volt, that is equal to IDRD. IDRD is what is that? Kn into VGS minus V threshold of the N mass, the whole square. That's your ID into capital RD plus VGS. Getting right? Getting right?
Yes,
Yes,
sir.
sir.
Then this 20 is equal to what is Kn into RD? What is Kn into RD? What is Kn for this case? 0.5 milliamps per whole square. RD is 17. So 17 into 0.5. Half of 17. How much? 8.5. Correct? See that milli and kilo will get cancelled. So 17 is in kilo ohm and this is in milli. So milli and kilo will get cancelled. So 17 into 0.5, I'm taking that number as 8.5. Correct? Correct, Shweta?
Yes, sir.
So then instead of 8.5, I prefer to take it as 17 by 2. Okay, so that will play with the integer. Correct? 17 by 2, you can take Kn into RD product, then VGS minus what is threshold? 1 volt.
1 volt.
Okay, then VGS minus 1, the whole square, plus VGS. Yes, adjust this equation to give the desired result. Okay, so then it is 20 equal to 17, okay, into VGS minus 1 whole square plus 2 times VGS divided by 2. Correct? Correct? Yes or no?
Yes,
Yes,
sir.
sir.
Then it is going to become 40 equal to 17 into V square GS minus 2 VGS plus 1 plus 2 times VGS. Simplify this equation. What is the resultant? Okay, so take the move the 40 to the right side, then simplify. So how many V square GS you will get from this? How many V square GS you will get? 17 V square GS you will get. Then 17 into 2, 34. Minus 34 VGS plus 2. So it is going to become minus 32
32.
VGS. Correct? Getting Shweta?
Yes, sir.
Then constant will be 17. 17 into 1. 17 minus 40 will be 23 equal to 0. Getting? That's your equation. Following right? Following right?
Yes, sir.
Then the equation is 17 times V square GS minus 32 VGS minus 23 equal to 0. That's the equation. So immediately keep an eye on the characteristics. Device is on only for VGS more than 1 volt. So the right root will be falling beyond 1 volt. Okay, VGS more than 1 is the right root. Less than 1 volt is the wrong root. Then solve for the VGS. VGS is equal to yes. Directly, can you tell me by using your calculator what are the two roots? Otherwise, you need to go by this way. It's going to be 32 plus or minus root of 32 square. Okay, plus 4 into 17 into 23 divided by 2 into 17, that is 34, will give two roots of VGS. What are the two roots? As per my design, I remember one root. It's 3 is one root, another root. Yes, I'm expecting 3 as one root. Hope you're getting that.
Sir, through calculator, 1 root 2.44, sir.
Another root
Minus 0.56.
0.56.
Yes,
1
sir.
minute. Any mistake committed? Correct. Okay. So I set VGS equal to 3 volt. Okay, myself, and VGS equal to 3 volt. What I will get is VGS minus V threshold will become 2. 2 square is going to become 4. Then 4 into 1.5, sorry, 0.5 is 2 milliamps. Okay, that's a mistake I committed. The mistake I committed is this. So I set myself VGS equal to 3. Because of that, this point is going to become 3. And I know this is 20. I know this is 3. Therefore, the net drop is going to be only 17. In the calculation of RD, I made 17 by 1 milliamps instead of 17 by 2 milliamps. Because actual current I assumed is 2, but wrongly calculated. That's why it is not matching. So whatever the answer you are getting is perfectly all right. Okay, some mistake in my design, but this is correct. Okay, but circuit will verify. Correct? Are you getting? So that's a mistake in the design itself. Okay, but that's a way. Okay, so but device is still on. Correct?
Yes, sir.
Even
Yes,
if we
sir.
commit a mistake, device is always going to be in saturation, not an issue because the gate and drain are shorted. That's what you're getting. What is the next digit, Shweta? After 2.44, what is the next round number? It is
No, sir. The next It's 2.437 something,
Okay,
sir.
you made it 2.4. Okay, fine then.
Yes.
Okay, that's a rounded number. Okay, then with this data, you get back to the circuit. Circuit will correct it. Okay, so then what we have is NMOS with the gate and drain shorted. Then we have the resistance 17 kilo ohm, and this point potential is 20 volt. Problem is about the current. Okay, you got the potential. What is the potential VGS?
2.44.
2.44.
2.44 volts. Okay, it's a rounded number, right? Then the gate terminal will be at what potential? 2.44. Then this point will be at what? 2.44. Then what's a drop across 17K? 20 minus 2.44, it is going to be 17.56 volt. And tell me what's a current now? ID. Problem is ID only because you know it is always in saturation. Because your VDS is same as VGS, that is 2.44, which is always going to be greater than or equal to the VDS. Pinch of that value is equal to 2.44 minus 1. Okay, which is nothing but 1.44 volt. Pinch off will happen at here itself. So VDS is greater, so it is always going to be in saturation. Yes. Yes, what is the current ID?
1.03 milliamps.
Milliamps. Are you getting Dinesh? Same number?
Yes, sir. 1.03.
Okay, then how to verify this current means? Okay, so then you have the equation. So that's a way to verify. If you don't believe it, another way, this is a circuit way. What we have done is circuit way. This is the mass way. Using the mass thermal characteristics, so we know ID equal to for the given VGS Kn into VGS minus V threshold of N mass the whole square. This is simple. Device is in saturation. Kn is 0.5 milliamps per watt whole square, and VGS we calculated 2.44 volts minus threshold known 1 volt the square. Yes, tell me what you're getting now. Both the answer should match. Otherwise, you have to make this accurate, more accurate. If there is a mismatch, this is N mass way of getting current. At least it is closer to it.
1.0368, sir.
milliamps. There is a small mismatch, but you can discard the negligible mismatch. Here also it is 1.03. What is this exactly? What is this exactly? 17.56 by 17. Exact number, please, Sweta.
1.03294.
Okay, 29. Okay, milliamps. See the difference? Because of not choosing exact value of VGS, this mismatch will happen. But you can appreciate that whatever the current you are getting is almost matching with the NMOS current. Okay, correct? Correct?
Yes, sir.
Yes, the big doubt will come. Which route you should consider during examination? Which route you have to consider during examination? Because here you will give the answer as 1.037 if it is up to 3 decimal places. If I ask here, okay, up to 3 decimal places, you will give the answer as 1.033. They are different, correct? 1.033. Okay, and here 1.037 you will give the answer, correct?
Yes, sir.
Then which one you will feed as an answer in the exam?
1.037.
Yes, Sweta?
So through device thing from the
That is
formula.
1.037 you will feed?
Yes, sir.
Okay, it's not about this. So actually both are going to be same answers, provided you have to increase the digits for your VGS. If you increase the digits, both answers will match. It's not about, I don't suggest anyway. So if you want to make your result accurate, make your VGS accurate, then both will give same answer only. Okay. Tell me what is your VGS accurately. So make your VGS 4 digits instead of truncating this to 2.44, yes, better go for the accurate answer. Tell me what is the accurate answer here. 2.43 something you said, Sweta.
1 minute, sir.
Yes.
43742.
742, right?
Yes, sir.
Yes, you have to take this voltage at least. You take 2.4374. If you take VGS equal to 2.4374, then redo it. So instead of 2.44, you take it as 2.4374. We'll see. So here you are taking 2.4374 means this point is also going to be what? Same potential. Therefore, this point will be 2.4374. Tell me what's the difference now? 20 minus this. 20 minus 2.4374 will be the accurate data.
17.5626.
Now tell me what's the current ID. 17.5626 by 17K. 1.03
03309.
31 milliamps, correct?
Yes.
Correct. So up to 4 decimal places, you are getting this answer. And take this data, that's your VGS, 2.4374 to this equation now. Instead of this, you use 2.4374. Now tell me what's the current. 2.4374 minus 1 is 1.4374, the whole square into this. Tell me what is the number you're getting.
One point 03305.
0.5. Okay.
Yes.
Yes, sir.
It's one right anyway.
Yes, sir.
Both are same now.
Yes, sir.
So who is creating the problem?
VGS.
VGS. So keep the data accurate. Both will give same answer. So then only you can. So it's up to you. So which route I'm recommending is circuit route is the one I'm recommending always. Okay, right? Because in the circuit, you will, if any mistake you are committing means the circuit will help you to correct it. But when you play with the equations without seeing the circuit blindly means you can't do the verification properly. I don't suggest this route. Okay, right? So books may give this route, but I don't suggest this way. So go by this way. Okay, so once you get VGS, then have an habit of playing with the circuit. Okay, if the answer is having mismatch, then try to increase the accuracy of your answer for the VGS. Then you will get more accurate current result. Okay, both are going to yield the same currents, either circuit way or device way. Getting Sweta?
Yes, sir.
Getting Dinesh?
Yes, sir.
Okay, so that's a way so to answer this kind of problems. Okay, I'll give one more interesting example similar to this. So you're going to answer this. So where NMOS is having this specs, its Kn is 1 milliamps per whole square. Its threshold is 1 volt. The current given is 5 milliamps. The current given is, so I'm connecting a current source of 5 milliamps. Okay. Problem is this: find the potential VD in the given circuit. That's all. Yes, try. Find the potential VD in the given circuit. What is the only hint where you need to begin the problem?
BD is equal to VGS. Okay, sir.
Yes, VD equal to VGS.
ID is given.
Okay, ID is given. Where to begin? You have to begin with gate and drain or simply in shorted connection devices operating in
Saturation.
saturation. Yes, devices clearly, NMOS is clearly operating in saturation. Already you have the equation for ID versus VGS. Yes, find out the potential VD. Take 2 minutes and give the answer.
Sir, 3.236, sir.
Yes, Dinesh, getting the same
No, sir.
or completed?
So 1 minute, sir.
Okay.
Yes, sir.
What is the answer getting, Shweta?
3.236.
3.1326, right?
No, sir. 3.236.
Okay. 236 volts, correct?
Yes, sir.
As your VD. Okay, we'll check.
So 4.291,
4.291.
291.
Okay. Okay, you have given two answers. I'm going to check in an easy way. I know if the device is in saturation, it is going to obey the equation Kn into what? VGS minus V threshold of your NMOS, the whole square. That's all. I know very well the device is in saturation. So you have given the different values of VGS. So that means you have given VD, that is nothing but anyway VGS. So I'll substitute and then, so VD is nothing but VGS. So then we'll see what's ID. Yes, take VGS equal to 3.236. Now tell me what's your current, Sweta. ID equal to 1 milliamps per whole square into the VGS minus 1 whole square. Substitute your VGS. So tell me what is the current you are getting. That's a verification. If you're not getting the current again as 5 milliamps, okay, you know very well the current in the channel is 5 milliamps because the gate current is always 0 milliamps, correct? Getting?
It's 4.9999.
Yes, that's wonderful then. It's closer to 5. Yes, according to you, Dinesh, let me substitute your sample, that is 4.291, and definitely you're not going to get 5 milliamps because I don't know which answer is correct. This is what we do to verify it. For the given circuit, only one option, one VGS will strike the balance. What is the number you're getting, Dinesh, now?
So it goes over 9, sir.
Yes, greater than 9 milliamps. So definitely this is the wrong answer, correct? This is okay, correct?
Yes, sir.
Okay, so then yes, without checking, you should not go with an answer. Okay, right? So it's a beginning only. So in fact, in biomedical paper, they played very nicely. I'll show that what problem they have constructed in GATE 2021. Okay, you can see that. See this problem, visible, right?
Yes,
Dinesh,
sir.
Yes, sir. Yes, sir. Visible.
that's a problem given for biomedical students. Okay. In fact, such a problem, such a kind of problem never happened for easy EEE instrumentation also. Okay, that is a level of expectation. Okay, so the level of questions will be same as your easy level only. Okay, because for the FET's highest level is happening in easy only, so you have to prepare to this level only, just a sample. Okay, so because you should not feel in the middle of the subject. Okay, so people won't ask this much level. Understand, Dinesh?
Yes, sir.
Okay, yes, let me do it. Try once again this. I'll give the idea, Dinesh. Already it's a familiar route. Probably you'll feel familiar, Shweta, now. Are you feeling it? The route is very clear now, right?
Yes, sir.
What is the route
ID.
once again? Finding VGS.
VG.
Correct. So the current is very clearly known as 5 milliamps. And now let me check what route you played. Okay. So what is the device is very clearly known to be in saturation, Shweta, right? NMOS is clearly in saturation. Then you will exploit the equation ID equal to Kn into what? VGS minus V threshold, correct? Of NMOS the whole square, right? ID is given. How much? 5 milliamps. And Kn is given. How much?
1 milliamps per
1
volt.
milliamps per whole square. Who is only unknown?
VGS.
VGS minus. So this is 1 volt, correct? Then tell me what you did after the step.
Took that 1 milliamps to this side, sir.
Left side.
Yes, sir. Division. Yes, sir.
Okay, then result is 5. Milli will get cancelled. It is going to be 5, correct?
Yes, sir.
Then what you did?
Expanding that V square Gs.
Yes, what you did here? Dinesh, what you did here?
Same, sir. Expanded, sir.
Why expanding? Why can't you apply root on both sides? That is more intelligent play, right? Yes,
Yes, sir.
Shweta.
Yes, sir.
Then what is the result? Root 5 is equal to VGS minus 1. The problem is over instantly. Why unnecessarily going for two roots? Getting Shweta?
Yes, sir.
Then what is your answer? That's all right.
Yes, yes,
Root
sir.
5, you
Yes,
know.
sir.
What is root 5?
2.236.
Okay, then 1 plus it is going to be 3.236 volts. Straight away, you got the answer. Yes, Dinesh, you should not commit a silly mistake like this. Yes, root is very important. So you should have applied the root because right hand side is square, left hand side is only a number. Apply root for the entire equation. So it is going to become root 5. The square will get cancelled. When you not to go for a second order equation, you can simply go for the answer instantly. Getting Shweta?
Yes, sir.
That's a helping hand by the designer. Correct? Why current is given? For any other problem, you can pay like this also. Okay. Since the mind is already decided to go by expansion of VGS minus V threshold whole square. Because of that habit only, again you expanded without noticing that we can go for square rooting entire equation, then get the VGS instantly. Correct? Correct?
Yes. Yes, sir.
Yes. Okay. So a lot of small things will make your calculation rapid and complete the problem instantly. Okay. So that's how. So the practice will tell you when you bring all the things together, then it's possible to get the solution instantly. Okay. This is what exactly the gate is demanding from you. So at this point of time, I'm asking you, do you know what exactly gate means? What exactly gate means? Stands for? You already applied. What does gate mean? Yes, Dinesh, what is gate? Expansion of gate?
General aptitude test for
For
don't know, sir.
E for engineering, right?
Okay,
Yes,
sir.
it is.
Yes, Dinesh.
Sir,
Yes, you should say now clearly. Getting Sweta.
Yes, sir. Yes, sir.
It's a graduate, not general, graduate aptitude test. Okay,
in engineering.
for engineers in engineering. Right, we should know, right? Already we applied, right? Without knowing it, correct?
Gone out
Yes.
of my sir.
Yes, you should know that. Yes, what is
Yes,
is
sir.
that exactly the name? Okay, why it is given as a gate? It's a graduate. You are, yes, you are undergraduate. You are completing your graduation. Once you complete your Bachelor of Engineering. Okay, E refers as an engineer. You should say whenever you see the letter E, engineering only or engineer only. We should, right? BE. What is BE? Bachelor of Engineering, right? Yes, right.
Yes, sir.
Okay, so the E refers always engineering. Okay, so it's a graduate aptitude test in engineering only. So what I'm talking here is only that aptitude. I'm giving you an equation. So whether you go by aptitude way, so you are applying your basic skills of playing with numbers in engineering. Okay, that's what the examination means. Okay, right? You're playing with numbers. Okay, so for that engineering application, that's all. How quickly you play with numbers only we are testing. Okay, getting?
Yes, sir.
Yes, sir.
Yes. Okay, so yes, you should go by the root instead of okay, expanding VGS minus 1 whole square. And this is going to become lengthy. Instead of stopping the problem here, you're going to make the problem lengthy, right? Correct? Yes or no?
Yes, sir.
Yes, that is lengthy. And that too, remember that you're going to do all online manipulations only, online calculator manipulations only. So getting the equation, getting the two roots is not going to be easy. Instead of that, you can go for the right route by applying the root. Okay. Yes, that's the thing. So how we are going to manipulate that data is completely your way. Okay. So designer is not forcing. Okay. You have to force in the right way yourself. Okay. Is it right?
Yes, sir.
Yes, I'll give one problem from the recent year so that you will get the taste of the gate. Let me pick one from electrical, which happened in 2020. Okay, I'll give the problem in the next class. Okay, I couldn't trace it out as of now. Yes, I got it. So that you will have some hands-on experience. You can visualize how a problem is constructed in the gate level. Okay. Okay. So this is exploiting another fundamental. We'll introduce that fundamental here. Okay. Yes, try this problem. That is from K 2019. Electrical for 2 marks. Similar to the problem we have done, but little extra is given. So we'll use this problem, okay, to offer such a foundation. Hope the problem is visible. Yes, Sweta?
Yes, sir. Yes, sir.
Okay. Yes. So what is the extra data given? So for the NMOS, okay, E-type MOSFET in the circuit below operates according to the square law. So that square law means it's your ID versus ID equal to Kn into VGS minus V threshold of NMOS, the whole square only. That's a square law connection. Correct? Getting? All of you getting this?
Yes, sir.
Okay. Understand what is given first. Then what else is given? Threshold is given for the NMOS. What is new? What is new? This mu and Cox is new. And this W by L data also new. Correct? What is missing? What we are looking for? The moment we see NMOS, what we are looking for? The problem is very identical to the previous problem. But only problem is we are looking for the data Kn. V threshold is given how much? 500 millivolt, which we can take it as comfortably as 0.5. And Kn we are looking for, that Kn data is not given. Correct? Getting Sweta?
Yes, sir.
If that is given, we can complete the problem. That means the Kn data is a function of this parameters mu and Cox and W by L. So you should remember an equation. Okay, so which will be proved in electronic devices. For analog circuit, take this granted. Kn is nothing but half of mu n Cox into W by L. That's actually the one deciding the Kn, which is known as the transconductance parameter of the device. It is known as transconductance parameter of NMOS. Okay, Kn, because that is the one going to decide your transconductance. So the name, or simply the NMOS constant, you can say. So now mu n Cox is given, W by L is given. First, you need to understand what is mu n. So mu n is nothing but in the equation. So you need to understand this. Kn is nothing but half of mu n into Cox into W by L. Okay, where mu n, our NMOS is made up of what channel? The channel is made up of what material?
And
N material. So this mu n refers mobility. Mu refers mobility. So in N channel, who is your charge carriers?
electrons.
Electrons. Readings, Sweta. In
Yes,
P
sir.
type, it is whole. So this is talking about electrons mobility. Okay. Mobility of electrons or electron mobility. Okay. That is a data. Mu n refers electron mobility. Cox refers the capacitance of your oxide. Okay. With which you're going to isolate your channel from the gate metal. Okay. So this is where you're going to have your O2. That is your oxide. Correct. That's your O2 that is going to offer oxide layer that is going to make your capacitance. Okay, right? So that is called the capacitance of the oxide insulating material. That is the one insulating your channel with the gate terminal. Okay, so that metal oxide. Okay, so or simply the oxide forming the dielectric medium, forming the capacitance. So this is called as oxide capacitance. Oxide capacitance. And W by L in farads by default. W by L is nothing but the channel geometry, that is ratio between width of the channel, okay, width to length of the channel ratio, width to length ratio of the channel. That's how we call this, width to length ratio of the channel. Easy now? Getting?
Yes, sir.
Yes, sir.
Okay, then what is given now? You can go with the data given, calculate then. So what is given? Mu and Cox is given. W by L is also given. Okay. So it's a, remember it's an analytical paper. Okay. So mu and Cox usually never given till GATE 2019. They have given this data. Straight away they used to give Kn only. But surprisingly, they have given this data for the electrical students in 2019. So mu and Cox is given as 100 microamps per whole square. W by L is unitless because width is going to be usually in the micrometer technology as per the microelectronics and VLSI design. So width will be in micrometers and length also going to be in micrometer. But already we started working on nanometer technology. It may be given in nanometers in upcoming examination. Maybe either micro or nanometer technology. Depending on that, you can go for the dimension for width and length of your channel will be given. But anyway, this W by L ratio is going to be unitless because if it is meters, it is also in what? Meters. Correct? If you are building the MOSFETs using micrometer technology, then the width will be given in micrometer and length also will be given in micrometer. So the ratio will be unitless anyway. So that's what given in namesake in this, it is 10 micrometer per 1 micrometer. What is the result? W by L equal to 10. Ready? Sweta.
Yes, sir.
So W by L is given. So then you can have Kn. So what is your Kn then? Half of 100 micro into 10. So it is going to be half of 10 is 5. 5 into 100. Result is 500 microamps per whole square. Therefore, the Kn is 0.5 milliamps per whole square. Indirectly, the data of Kn is given. Easy? Clear, right?
Yes, sir.
Okay, yes, that's a extra play by the designer. So on the way you understood, okay, how to play with the data. Yes, for this, yes, you can play now. You can give the answer. What is the threshold for the NMOS? Threshold of NMOS is equal to 0.5 volts. Kn already we calculated by using half of mu n C ox into W by L as 0.5 milliamps per whole square. And current is given as only what? 5 microamps. So instead of 0.5 milliamps per whole square, better you take it as 500 micro because the current through the channel is also in micro. So things will be easy instead of milli. So that's your Kn. So we know the channel current because the gate current is always 0. So the channel current is your 5 microamps, correct? So given ID equal to 5 microamps, and we know devices in saturation because the gate and drain terminals are again shorted, correct?
Yes.
So therefore devices in saturation. So under saturation, ID equal to An into VGS minus V threshold of the NMOS, the whole square. So then ID is given as 5 microamps, that is equal to Kn is equal to 500 microamps into VGS minus 0.5 the whole square. Yes, rest is completely your control. Give me the answer. Because what is V out? If this potential is VGS, once you get VGS, what do you know? Gate potential. The gate potential is equal to V out. Therefore, gate potential is VGS. V out is equal to what? V out is equal to what? VGS only. Getting Dinesh.
Yes, sir. Getting.
Okay, yes, find the VGS and complete the problem. You know the route. That's why the practicing, okay, whatever the examples I'm giving will be exploited. The fundamental only will be exploited. Little extra push always he will make as a designer. He will never give copy paste problems. He will play with them only. Okay, so you'll pick the data accordingly and Okay, some extra statement also you will give. He said ignore channel length modulation. We never know what is channel length modulation till now. I have not yet introduced them also. He said ignore only, so don't consider that. Simply go for the normal way of getting the output voltage.
C, sir. Option C.
600 millivolts.
Yes, sir.
Yes, sir.
Yes, your choice, Dinesh.
C, sir. 600 millivolts.
It's easy now. You started playing now. This is micro. This micro will get cancelled, and 5 by 500 will become 1 by 100. 1 by 100 equal to VGS minus 0.5 whole square. And because of the new habit, what you did? Applied the root.
Yes, sir.
Okay,
Yes,
then
sir.
what is the left side? 0.1 then. Correct? 1 by 10.
Yes, sir.
Then right side is what? VGS equal VGS minus
VGS minus
0.5. Then what is
0.5.
VGS instantly? 0.6.
Point.
Then answer is 600 millivolt. Easy, right?
Yes, sir.
Where that play only in the Kn. He didn't give directly. He asked us to play with this equation. Understood? So once you know the
Yes, sir.
fundamental, so even the gate problems are going to be very easy. Gate is not tough, believe. Okay, so only if you don't have the fundamental to connect, you will feel tough. If you have the fundamental to connect, then it is going to be easy only. So what are the fundamentals exploited? Since gate and drain terminals are shorted for the NMOS always in what? Saturation. Then happily we can use that equation. Okay, threshold is given, but only play is Kn is not directly given, but indirectly given by giving mu and Cox, okay, for the device and W by L ratio of the device. With that, one can quickly calculate the Kn. Then we can play and help yourself not by expanding VGS minus 0.5 whole square. That will complicate things, okay, so that you can help yourself to complete the problem instantly. Fine. Is he right?
Yes, sir.
Sweta, getting?
Yes, sir.
Then I will create another example. Two identical NMOS transistors. MOS 1 I'm calling, another transistor MOS 2 I'm calling. So two identical transistors in all aspects, M1, M2 are identical in all aspects, means they have identical mu and Cox, they have identical W by L, they have identical threshold. Hope you understand now. Reading?
Yes, sir.
Yes,
Okay,
sir.
yes. Now they are connected this way. Source is connected to ground. This is connected to a 10-volt supply. I am connecting the gate and drain terminal shorted. Here also the gate and drain terminals shorted. I'm asking, I'm calling this as V out. Find the voltage V out. That's a problem. Find V out in the given circuit. If you want, you can take the data. MOS 1, MOS 2 are identical with threshold voltage of 1 volt and Kn is equal to 1 milliamps per whole square also you can take. Either I may give or I may not give. Okay, I'm giving, okay, because you're looking for, okay, I'm giving this. Later you can conclude without them also, the answer is going to be the same. Okay, because the answer is independent of your mu n, Cox, W by L and threshold voltage, but provided threshold voltage is greater than 1, sorry, that N masses, the two mass transistors will be in on condition if the VGS is greater than, 1 volt, correct?
Oh, no. Yes, sir.
Okay, that's a characteristics of the NMOS transistors. Yes. Yes, then But I said a clue. If gate and drain of a MOS transistor is connected, then device is always in
Saturation.
saturation. Yes, one data we know, one information you have. But problem is, what is the potential V out? So both M1 and M2 can be in saturation, correct? Yes or no?
Yes, sir.
If they are in saturation, definitely they're going to have a VGS. So this is VGS2 and this will be VGS. This will be VGS1, correct? Yes or no? So this will be greater than 1 volt. This is also greater than 1 volt because device is on, they are in saturation, correct? Getting?
Yes, sir.
Then what is the current in this device? For the given VGS1, what is the current here? This current you can call it as ID1. Correct? The same current is going to come here. ID1. And any gate current in the second device, M2? No gate current. Gate current is always equal to 0. Correct? Correct?
Yes,
And this current is ID2. Okay. Now the circuit says something. What the circuit says? As per the physical circuit connection, circuit says that ID1 cannot be different from ID2. Correct? This is by circuit way. The circuit says that ID1 is equal to, getting Shweta?
Yes, sir.
The circuit says ID1 is equal to ID2. Correct?
Yes.
That's where the problem begins. When the circuit says ID1 is equal to ID2 and both the MOS transistors M1 and M2 are in what? Saturation. That means they're going to follow the equation. What equation? They're going to follow Kn into what? VGS1 minus V threshold, okay, the whole square. That is equal to identical NMOS transistors. They will have identical Kn. Therefore, this is also going to have the same Kn, but the potential is different. VGS2 you can take for the second MOS minus V threshold of NMOS, the whole square. Since ID1 equal to ID2, the condition forced by the circuit, okay, then tell me what will happen for the two equations. Since they are in saturation, you can use saturation equation currents, and Kn will get cancelled. Getting?
Yes, sir.
Tell me what is your perception now. If these two currents are same and Kn and V threshold
VGS
are
also.
same, and finally you will end up with VGS1 minus V threshold is equal to VGS2. Cancel the square roots also. V threshold, correct? Yes or no, Sweta?
Yes, sir.
What's happening because of this? This V threshold and this V threshold will get cancelled. What is the only conclusion?
VGS1 equal to
Should be equal to what? VGS2. No other choice. Because who is making ID1? VGS1 is making ID1. Who is making ID2? VGS2 is making ID2. If ID1 equal to ID2, VGS1 can be different from VGS2? Cannot. Correct? That conclusion you can derive straight away by seeing the circuit, because both the MOS transistors are, okay, driving same current. Therefore, both should have identical VGS. Therefore, VGS1 cannot be VGS2 different from VGS2. Therefore, VGS1 should be equal to VGS2. That's another information we are getting because of circuit is forcing ID1 equal to ID2, and because of identical parameters Kn1 and Kn2, they are identical. Therefore, we can cancel. The problem is easy. If Kn1 and K2 are different, still we can derive a conclusion between VGS1 and VGS2. But they are not going to be equal. They will be little different if Kn1 and Kn2 are different. Getting the point, everyone?
Yes, sir.
Yes, sir.
Okay, since Kn1 and Kn2 are equal and V threshold of them also equals, because of identical MOS transistors, VGS1 should be equal to VGS2, then only it's possible to get ID1 equal to ID2. But problem is not about VGS1 and VGS2. Problem may be for them also, but problem is ultimately for what? V out. Correct? Yes or no?
Yes, sir.
Okay, we'll see how we can conclude the problem from this. Expect this kind of interesting problems. What is the potential here? 10 volt, right?
Yes, sir.
Okay, so these two are tied together and these two are tied together. Maybe this is the point potential. We call it as V out. Okay, now let us play. What is the potential here? This is mass 1 and this is mass 2. Am I right? Correct? That's how it is labeled. Okay, then this potential is VGS1. And since we have identical VGS, correct? Yes or no? Because identical currents. So this current is ID. This current is also ID. Since identical current, identical VGS. Then form a simple KVL in this path. Tell me what's your KVL. 10 volt is equal to VGS1 plus VGS2. That's all right. This is VGS1. That is equal to what? VGS. This is VGS2. That is equal to what? Also VGS. Then 10 volt is equal to what? 2 times
VGS.
VGS. Then what is VGS? That's how this simple the problem is now. How much potential VGS? 5 volt.
5 volt.
Yes.
Then your understanding is this. So here you're getting 5 volt. Here also you're getting what? 5 volt. For this 5 volt, it is going to force a current. For this 5 volt, it is going to force same current. So the two currents are equal. Getting now?
Yes, sir.
For any given Kn, for any given V threshold. But threshold is given more than one. So even you can calculate your currents. Okay. So both are having identical, even if you can use or not. Okay. Result is same. Okay. So now we can go for the current if this data is given. So 5 minus 1 whole square will be 16, 16 to 1 milliamp. So the current will be equal to, current will be actually equal to in the circuit. For the given
16.
data, 16 milliamps current will be here. And here also the current will be what? 16 milliamps. Numbers only to understand and appreciate. Okay, whatever we are doing is correct. Okay. So therefore, we are getting VGS equal to 5 volt. That is going to set such a current. We are able to conclude that ID1 equal to ID2. The moment hereafter ID1 is equal to ID2, VGS1 should be equal to VGS2. Straight away you can take the call and simply the 10 volt is divided equally into VGS1 and VGS2 as per the KVL. Therefore, tell me what's the potential at this point? What is the potential at this point? What is the potential here? 10 volt. And what is the potential here? 10. From 10, you are losing.
5.
What is this point potential then?
5 volt.
5. So what is
5
V
volt.
out then?
5 volt.
That's all. That's how we can conclude the problem. It looks little complex initially, right? Because no idea how we are going to meet the concepts and how we are going to conclude the problem. Initially, it is not giving any idea. Yes, Veita? Correct?
Yes, sir.
Initially, you had no idea, right? How we are going to approach and get the answer right?
Yes, sir.
Okay, so now it's very clear. Dinesh, kidding?
Yes, sir. Getting, sir.
So you can also proceed from this way. So what is the potential here? 0. So from 0 potential rises, what is this point potential? From 0 potential rises by 5 volt. What is the point potential? 5. If this is 5, this is also 5. Yes, anyway, either you can go this way or you can go this way. Result is anyway 5 volt only. Correct?
Yes.
Correct?
Yes, sir.
Yes. That's another interesting one. So now I will make it little better. Hope you can answer this. That's a final one. Today we are concluding little early. Okay, that's a final example for the day. Circuit is same. That's how people will take it to the higher level. Okay, once you understand something, yes, then you have to force yourself to the higher level. So I'm going to give only 5 volt now, small change, and this is 0. I'm going to connect again the gate and drain of this and gate and drain of this also. I may connect it like this. Okay, I may not show you that the top transistor gate and drain also connected together, but actually they are connected. Yes or no? Correct, Shweta?
Yes, sir.
They connected, right? They're sensing same potential, correct? That's what it means. So
Yes,
therefore, the top transistor is also in
5.
saturation, right? Because gate and drains are connected together, mean this is in saturation and this is also in what? Saturation. Both the transistors are in saturation. We're going to calculate V naught. So this is mass transistor 1 and take it as mass transistor 2. M1 and M2 are identical transistors in terms of mu and C ox and threshold voltage. And this is the statement I'm giving. Okay, so M1 and M2 are identical transistors in all aspects, except that I'll say this way, except that W by L of mass 2 is equal to 4 and W by L of mass 1 is equal to 1. So mass 1 W by L and mass 2 W by L. Getting now, Sweta?
Yes, sir.
So they are going to differ, correct? The two transistors are differing in terms of mass 1 and mass 2 differing only in terms of width to length ratio. In all other aspects, they are same. If that is the case, find the potential V naught. That's a problem. That's your example. I'll show the way you complete the problem. Okay, so bring the answer and then we'll discuss this problem in the next class. I'll give you an idea. Again, the two transistors are in saturation, but as per the circuit, this current is ID1 for the given VGS1, correct? There is a potential VGS1 that is going to make the current ID1. And there is a potential VGS2 that is going to make the current what? ID2. Getting? Because both are in saturation. And this current is anyway ID1. And this current is 0. Therefore, again the circuit forces ID1 equal to ID2. Correct? Yes or no?
Yes, sir.
But VGS1 not equal to VGS2. Tell me why?
Because of Kn.
Because they have different Kn, correct? Even though they have, the beauty is, even though they have different Kn, they have to have the same current. Then how the problem goes? Okay, ID1 still equal to what? ID2. Then start building the problem here. ID1 still equal to ID2. Okay, and both the MOSFETs are still in saturation. M1 in saturation, M2 also in saturation. Use the saturation equation. So then you'll write Kn1 into VGS1 minus V threshold, the whole square you will get. V threshold given? Not given. Take it as 1 volt. V threshold is given as 1 volt. Take that. Without that, we can't complete the problem here. So V threshold is given as 1 volt. Okay, for both the mass transistors. And this is Kn2 into you will get VGS2 minus V threshold of N mass, the whole square you will get. Correct? Now, who is higher? Whose W by L is higher? Kn, M2 or M1?
M2, sir.
M2 is higher. Okay, that means I'll go for Kn2 by Kn1. So tell me what is Kn2 by Kn1? What is Kn2? Half of mu n C ox W by L of mass 2, correct? Because other parameters are identical. And this will be half of mu n C ox W by L of what? First mass, correct? Now tell me what is the remaining? What is the remaining? This will get cancelled. This will get cancelled. What do you get then? Ratio between the two transconductance parameters. Simply ratio between the W by L of the two mass transistors. So what is W by L2? 4. What is W by L1? 1. What is the ratio between them?
4.
4 is the ratio. Yes. So then this is known, means then you can modify this equation as what? VGS1 minus 1 volt, this whole square. Then take Kn1 to the right side. It is going to become Kn2 by Kn1. That is equal to 4. You can get VGS2 minus 1 whole square. I will stop here. What is your job? What is your job?
Find VGS.
VGS1 and 2.
Yes, you need to find out what is your VGS1, what is your VGS2. Okay, that's how we need to strike a balance for this. Easy? Getting?
Yes, sir.
So that means you need to find out. So what VGS1 and what VGS2 will strike a balance. This is actually having two unknowns, right?
Yes, sir.
Then how we can solve for VGS1, how we can solve for VGS2? And this is going to give infinite solutions, correct? If you fix some value for VGS1, there is going to be a value for VGS2, correct? Yes or no? So it's an infinite solution problem. Then we need two unknowns, means we need two equations. So we have only one equation. Another equation already you are familiar. Go by KVL in this path. But the KVL, as per the KVL, we know 5 volt is equal to spent as VGS1 plus what? VGS2. Getting? Getting? Getting,
Yes,
Shweta?
yes, sir.
So already we know that KVL, that is going to be the second equation. So second equation is 5 volt is equal to sum of VGS1 plus what? VGS2. That's a equation number 2. Yes, we have two equations, two unknowns. Comfortably we can solve for VGS1 and what? VGS2. Then after finding them, you can still confirm ID1 equal to ID2. Okay? By having some value for Kn. So assume by having some value for mu and Cx. Okay, have some value for mu and Cx. With that, you know, because W by L is given, therefore you need to have mu and Cx value only. Take it as 100 microamps per whole square. Okay, so with that, you find the two currents and confirm they are same after getting VGS1 and VGS2. Okay, getting Dinesh, getting Shweta.
Yes, sir.
Yes, sir.
Okay, so idea given. So build and try to give the answer, accurate answer. Okay, so in the next class. Okay, fine. Hope it is clear.
Yes, sir.
Yes, sir. Please.
Okay, so if we have any other doubts, you can discuss. With that, we'll conclude the day. So then, thank you everyone. Good night.
Thank you, sir.
Thank you.